Hello, good morning, thanks for coming. So today we will have a homework 5 solution. So it will be a super short tutorial. Let me explain the questions and answers. So this is homework 5. So in homework 5, there are 5 questions. The first one is a simple Markov chain problem. So we have the following Markov chain, and then somehow we want to show that for this Markov chain, there is a unique stationary distribution, and then we want to find out what it is. So for the first step, ah, no, not this one. This is just a simple example to find out the behavior of a Markov chain. Yeah, so it's not that one. So so first of all, suppose that initially we are uh, at the initial state, we are having probability 1/2 to be in this state 1. So this is the initial case. So we want to find out what is the chance that the first time x0 is equal to 1 and then the next step x1 is equal to 2. So what will be the chance of this one? So by intuition, so we are having 1/2 chance here initially, and then after that we need to have only 1/4 of this chance to go to state 2. So in such a case, the answer should be 1/8. And if we want to argue this formally, then we can use the conditional probability to help. So this is the probability that we want to find, and then this can be computed by finding what is the probability of x0 is equal to 1, which is known, multiplied with the probability of x1 is equal to 2, given that x0 is equal to 1. So given x0 is equal to 1, the chance that x1 is equal to 2 will be this 1/4 from this graph. So the answer for this one is 1/2 times 1/4, and it is equal to 1/8. And then we can do one step further. We want to find out what is the chance that x0 is equal to 1, at the same time x1 is equal to 2, and at the same time x2 is equal to 3. So this one can be computed by us. So I've missed some detail. So we want to find out what is the chance that, so forget about the formula here, this is wrong. So the chance of getting this one is exactly the same as there is half of chance here, multiplied with 1/4 chance here, and then multiplied by 1/3 chance here. So in the end, it is equal to 1/24. Okay, so somehow this is sorry, this is incorrect. So I'll make a change here after the tutorial. Okay, now for question 2, so we have this Markov chain. So we want to find out. So this time we want to find out that what is the stationary distribution for this Markov chain. So first of all, we need to show that, okay, so as required by the homework, we want to show that it is aperiodic and irreducible. So we are going to show these two things separately. Aperiodic, actually, we want to show for each state, it can come back to itself in irregular number of steps. So it is not always a multiple of some number. So if you want to, so we can check each state one by one. For state 0, it can come back in 1 step, and it can also come back in 2 steps. And similarly, for state 2, it can come back in 1 step, or it can come back in 2 steps. So 1 or 2 means that it is not, so this is like the greatest common divisor of this one is only 1. So it is not going to be a certain multiple of integer greater than 1. So state 0 and state 2, these two states by themselves, they are aperiodic. And for state 1, it can come back to itself in 2 steps. Of course, it can come back in 4 steps and 6 steps and so on and so forth. But then we also observe that it can come back in 3 steps. So by seeing that there is a way that it can come back in 2 steps or 3 steps, the greatest common divisor of these two numbers is equal to 1. So again, we show that these two states, this state 1 is also aperiodic. So when all the states here are aperiodic, yeah, this is the GCD part, then it means that the whole chain is aperiodic. So this is the first part. We show that the chain is aperiodic. And then for irreducible, we want to show that every state can reach any other state, including itself. Okay. Now, this is a simple chain that we see that there is actually a cycle we can find from 0 to 1, 1 to 2, 2 back to 1, and then 1 back to 0. So there's a cycle here. This cycle travels all the states. So it means what? It means that every state can reach any other state, including itself. So by definition, this is irreducible. Now, when the chain is aperiodic and irreducible, we know that it has a stationary distribution, and this stationary distribution is also unique. So we can find the stationary distribution by solving this set of linear equations. So when there is a stationary distribution, let's say it is P0, P1, and P2, then what we know here is that in the next state, the chance that we come back to this P0 could be either we from P0 to go back to itself, or from state 1 you go from this one. And then because it is stationary, it should be equal to P0. So we will have P0 is equal to 0.1 times P0 plus 0.7 times P1. And similarly, we have this one and this one. So solving this set of linear equations, there are three variables, three unknowns, but then actually we need to have a fourth one because this is like somehow a degenerate system. We have a fourth case such that the sum of P0, P1, and P2 is equal to 1. So together with four equations, we are going to solve them and then get a unique answer. So we will have P0, P1, P2 to be in the ratio of 14, 18, and 9. So any case with 14, 18, and 9 in the ratio will satisfy the above formulas. And then together, we want the sum to be equal to 1. Then we normalize them by dividing it by the sum of this 14, 18, and 9. So we divide this by 41, and then we get the result. So this is question number 2. Now, question number 3 is a random walk on a triangle. So we have 3 vertices. They have an edge, and then this is a random walk on it. And then we want to study the behavior of this random walk. Let's pick, so we assume that we start at a certain vertex, let's say vertex 1. And then we let pk to be the probability to go back to vertex 1 after exactly k moves. And then we want to find out what are the values of P1, P2, P3, P4, P5. So we are at state 1 here. So obviously we know that after one step, we must either be at state 2 or at state 3. So there is no chance that we go back to state 1 after one step. So P1 is equal to 0. We know this. But how about the other cases? So this is not a difficult problem. So we let P to denote the transition matrix, which is like this. So from state 1, there is 0 chance to go back to itself, half of chance to go to 2, half of a chance to go to 3. And similarly, at state 1, at this state 2, there is half a chance to go to state 1, half a chance to go to state 3, no chance to get it back to itself, and so on and so forth. So this is the transition matrix of this Markov chain. And then we use x0 to denote the initial distribution. So we have, initially we are starting at vertex 1. So there is all the probabilities we are here and none of the probabilities here. And in order to compute the little pk, we want to observe that, we just need to observe that we can find out this distribution xk after exactly k moves to be equal to, we multiply the initial distribution with the transition matrix to the power k, p to the power k. So after doing this step one by one, so we will have xk to be a probability distribution, and the first term here will correspond to the pk value, So we can solve it one by one, and then we see that these are the results. Indeed, there is a certain kind of a pattern here. So the bottom part seems like it is always a 2 power, and the top part is somehow interesting. Yeah. So is there a way to find the general form for this pk? And this is not required, but then you can, if you know how to solve recurrence, then you can solve this. So first of all, we observe that pk satisfies the recurrence relation as follows. So as mentioned, p1, we know that it is equal to 0. But then we claim that pk is equal to the half of a chance of 1 minus pk minus 1. Now, what is pk minus 1? Pk minus 1 is the probability that we are here at state k minus 1. So if we are here, then in any case, then we cannot come back to itself. But on the other hand, if we are not here, either here or here, there will be the same probability, 1/2 of a chance to go back to itself. So in that case, we can express pk as 1 minus pk minus 1, which is the chance that we are not at state 1. And then for all the probabilities here, there is 1/2 of a chance that we can go back to state 1. So we will have this pk is equal to this one. Then we have this set of recurrence, and then after solving it, then somehow we can get this closed form. So pk will be equal to 1/3 plus 2/3 multiplied by minus 1/2 to the power k. So by substituting, let's say we can check a few terms to see whether it is correct. So when k is equal to 1, what will happen? When k is equal to 1, this is minus 1/2. Multiplied by 2/3, we get minus 1/3. And then adding up together with 1/3, we get 0. So p1 is 0, so it is correctly computed. And let's say k is equal to 2, what will happen? So when k is equal to 2, this is going to be 1/4. 1/4 multiplied with 2/3, we get 1/6. 1/6 plus 1/3, we get 1/2, and then it is agreeing with this one. So indeed, this is a formula to compute pk for all the terms of k. Okay, so finally we have question number 4. Question number 4 is a gambler's ruin problem revisited. So, but this time we are not using a fair coin. This time we have a biased coin, so that we are more likely to lose than to win. So there's 1/3 chance that we will win $1, and then there is 2/3 chance that we are going to lose $1. So this game is not favoring us. We want to compute what is the chance of winning in this game. But then before we do anything, we establish a following fact. We let WT to be the winnings after T rounds. And then we want to show that the expected value of 2 to the power WT is equal to the expected value of 2 to the power WT plus 1. Okay, so it turns out that if we make 2 to the power of the winnings that we have, the expected value will remain to be the same. So how can we show? Okay, so the first part here is, well, let us discuss this in 2 separate cases. Because we are playing with this game, so we play until a certain player bankrupts, doesn't have any money left. So first of all, when some player goes bankrupt, then what will happen? Then the winning at state T will be the same as the winning at state T plus 1. The reason is that the money will not change anymore. If these two are having the same value, so of course, expected of 2 to the power WT must be equal to expected of 2 to the power WT plus 1 in this case, because these two are not random anymore. They are always the same value, so they will have the same expected value. But other than that, when none of the player goes bankrupt, we will still have the next round to play. So in this case, let us compute this related term. What is the expected value of 2 to the power WT plus 1, given that the current winning is WT? Okay, so for this case, it is easy. Okay, because we now know that the current winning is WT, so there are going to be 2/3 of my chance, so that in the next step, the WT plus 1 value will be equal to $1 fewer. And 1/3 of a chance, my money that I will have will be increased by $1. So in such a case, we have this one is equal to this term. And notice that this is T, WT, and then this whole term minus 1. So this minus 1 is not inside this T minus 1 here. It's not like that. So after doing some simplification, we will find that these two actually adds up to 2 to the power W of T. But we know that, so by the conditional expectation formula, we know that the expected value of 2 to the power WT plus 1 is the same as the expected of 2 to the power T plus 1 given WT. And for this one is equal to 2 to the power T, WT. So we just replace this one by 2 to the power WT, and then we get our result. So what does that mean? It means that no matter what case happens, these two terms are always having the same value. Okay? Okay, now we are about to analyze the gambler's ruin problem. Suppose initially you have only I dollars, and then your opponent is having N dollars. And then what will be the chance for you to win? Notice that the game is not fair. Okay, so what will be the chance of you winning? So let's see. So we let P to denote the chance of winning. And then again, as in our analysis in the lecture slides, we will assume what happens. We assume that T tends to infinity. So we are going to play many rounds. So when T tends to infinity, one of the player will go bankrupt. So in such a case, there will be P chance for you to be in the state of winning N dollars, and then there will be 1 minus P chance for you to be in the state of losing I dollars. Is that okay? So expected term of 2 to the power WT will be equal to, there is P chance with the value WT is equal to N. This is the case that you are winning. And with 1 minus P chance, you will have the WT value to be minus 1. Is that okay? Now, but then by the result of 4a, we know that expected of 2 to the power WT is the same as expected of 2 to the power WT minus 1, WT minus 2, and so on and so forth, right? So in that case, it is equal to expected of 2 to the power W0. Now when when this T is equal to 0, W0 is the winning that you have initially, which is you are winning only $0. Initially, you do not gain, you do not lose. Yeah, this is the initial state. So in such a case, 2 to the power 0 is equal to 1. So this is what we have. So we have everything. So we will now having P times 2 to the power n plus 1 minus P times 2 to the power minus I is equal to 1. So after solving this, we will have P is equal to the value like this. 2 to the power I minus 1 divided by 2 to the power n plus I minus 1. Okay, so what does that mean? It means that the chance that we are winning is going to be exponentially small. Okay, even if the other player has some money more than I do, let's say $1. Actually, $1, does that make sense? Let me see. I dollars, $1. So I'll need to double check whether this is really correct. Okay, so then in that case, yeah, somehow the solution is obtained by solving the equation. I will double check with this one and then send you a corrected slides if there are any mistakes after the tutorial. So yeah, that's the end for today. Yeah, thanks all for coming. Yes. Yeah, hope that it is correct, but somehow I feel it is rather strange. So it looks like if I have just $1, your opponent has just $1 and you have $10, what will happen? Yeah, this is something strange. I'll figure it out and then give you a correct solution after today. Okay, thanks for coming. So on Thursday, we will talk about homework 6 solution. So see you again on Thursday. Okay, that's all. Thanks.